today let's discuss another problem. Write the equations of motion in S domain for the given system and determine the transfer function. So here a mechanical system is given. Okay. So basically our first step is to identify the nodes. Nodes are the meeting point of elements. So if you look here, you can see like we have a spring with the stiffness K and a dashpot with frictional coefficient B2 connected in series, right? So the meeting point of these two elements is a node, but in that particular node we don't have a mass element, right? So for that what we need to do is we have to consider, or we have to assume a mass element over here between K and B2. But since in reality such a mass is not there, such a mass element is not there, you have to consider its actual mass to be 0. Okay, so we are going to redraw this particular system like this. So we have assumed a mass element between K and B2 because the meeting point of this spring and this dashpot is a node. As we don't have a mass element over there, we are assuming a mass element at the meeting point of K and B2. But since in reality such a mass element is not there, so we have to consider the actual mass of this particular assumed element to be 0. So we already have a mass element with mass m in the given system. So the assumed mass is considered to be, say, m1. So along with m1 you have to keep in mind that this mass m1 is 0. Okay, so when you assume this particular mass element, you have to assume its displacement also. Already we have a x of t over here, so the displacement of the assumed mass element is x1 of t. Okay, so now we are going to draw the free body diagram of each mass element. So firstly we are going for m. So we have marked the mass element. Inside the block we have written its mass, which is m, and above that we have marked the displacement of that particular mass element, which is x of t, and that is given in the question, right? And again, if you look at the question, we can see that the applied force F of t is acting on m. So in the free body diagram we have marked the applied force F of t, which is in the outward direction. Okay, now we are going to mark all the opposing forces. So definitely there will be an opposing force due to the mass m itself. We will mark it as F suffix m, and its direction will be inward, right? Again, look at the given system. There is a frictional element, say representing B1. This B1 actually represents the frictional force between the mass and the ground point. So that will act as a opposing force. So that opposing force is marked as F suffix small b1. Since it's opposing force, it will point inward. Again, if you look at the given system, dashpot B2 is connected to M. So definitely there will be an opposing force due to this dashpot. We will mark it as FB2. So these are the opposing forces. Then how will you write Fm? Fm is equal to the mass m into d square x of t by dt square. Here x of t is the displacement, and Fb1 is the frictional force associated with m only, right? So Fb1 equal to its frictional coefficient b1 into d by dt of displacement. Here displacement is x of t, so d by dt of x of t. So what would be Fb2? Here B2 right? So you have to go through the modified diagram. Here we can see like B2 is actually connected between this M1 and M, right? So what we need to do is we have to consider both the displacements. So which displacement to be written first? Right now we are considering the free body diagram of M, so its displacement should be written first. So if B2 equal to its frictional coefficient B2 into d by dt of x of t minus x1 of t. Okay, so we have to consider both the displacements. Since we are considering mass M right now, we have to write its displacement as the first one. So x of t first, that minus x1 of t. Okay, now by applying D'Alembert's principle, we have sum of total opposing forces is equal to sum of total applied force. So sum of opposing forces is Fm1 plus Fb1 plus Fb2, that is equated to the applied force. Now substituting values, we have this particular differential equation. So once we have the differential equation, we have to take Laplace transform on both sides. So we have taken Laplace transform on both sides, right? Then we are bringing the terms of x of s together and x1 of s together, right? So that would be equation number 1. Now we have to go for the free body diagram of M1. So when you draw that free body diagram, inside the block you need to mark M1, but at the same time you have to mark it as 0, because in reality we don't have such a mass over there. Okay, now why we are drawing that particular mass, or why we are assuming that particular mass? Because we have to get the opposing forces there correctly. So in order to get these opposing forces at the meeting point of the elements, or at the each node, we need to have mass elements. Okay, fine. So look at the modified block diagram. So if you look at M1, you can see like the spring with stiffness K is connected to M1, as well as the dashpot with frictional coefficient B2 is also connected to M1. So we have those two elements connected to M1. So we will be having opposing forces due to this K and B2 at M1. So free body diagram of M1, we have marked the displacement x1 of t, then Fk is the opposing force due to the spring with stiffness K, and we have Fb2, which is the opposing force due to the dashpot with the frictional coefficient B2. Now Fb2, as we have seen earlier, this B2 is connected between M and M1. So we have to consider both the displacements. So right now we are discussing about M1, and hence we have to write the displacement of M1 first. So we have Fb2 equal to B2 into d by dt of x1 of t minus x of t, and Fk is equal to stiffness into its corresponding displacement x1 of t, right? So K is just connected to M1 only, so we have to consider the displacement of M1 only. So Fk equal to K into x1 of t. By applying D'Alembert's principle, we have Fb2 plus Fk equal to 0. Here we don't have any direct applied forces, so the right hand side is 0. Substituting the values, so this is the differential equation we have, and now we are going to apply Laplace transform on both sides. Okay, so B2s into x1 of s minus x of s plus k into x1 of s equal to 0. We are bringing x1 of s terms together and x of s terms together, so we have x1 of s into B2s plus k minus x of s into B2s equal to 0. So here we are going to find the transfer function x of s by f of s. So the displacement term that we need is x. We don't need x1 terms. So here we have to, or we need to eliminate this x1, and our expression should contain only x displacement terms. So here what we are going to do is we are going to write x1 of s in terms of x of s. So x1 of s equal to b2s by b2s plus k into x of s. Let it be equation number 2. Now we have to substitute this equation 2 in equation 1. So on substituting equation 2 in 1, we will get x of s into ms square plus b1 plus b2s minus b2s whole square by b2s plus k into x of s is equal to f of s. So taking LCM and multiplying, and finally we will find the transfer function x of s by f of s, which is equal to b2s plus k by ms square plus b1 plus b2 into s into b2s plus k minus b2s whole square. So this is the final answer.